We just moved into the world of electricity, right? And so first of all, we introduced one of the most fundamental ideas in physics overall, the idea of the electric field, right? So and we introduce it as if you take small positive probe charge, calculate or measure force acting on the charge, and then if you take a ratio of force versus charge. So that's how we introduce the idea of the electric field. Then from here immediately follows one of the most fundamental formulas in physics, right? Electric force. So if you know the charge, multiply it by the value of the electric field at the point where the charge is, and that will be electric force. Then, of course, we introduce electric force acting between 2-point charges. Coulomb's law, everyone knows that, F equals KQQ over R squared, right? Then, just recently, in the previous week, we started switching to the energy approach. Since I'm here, so I decided to add this formula also, since it's kind of connected to the system. So, and we introduced the electric potential energy, which is energy of interactions. These describe interactions, these also describe interactions. This is a vector quantity, this is the scalar quantity. So potential energy of interactions of 2-point charges. KQQ over R. So the difference only in downstairs in the first power, in the first power of R. Then, if you have a parallel plate capacitor, we introduce it properly. Electric field, of course, inside is uniform. Expression for the electric field, maybe I should have added it. So electric field equals to surface charge density divided by epsilon naught. And so now, if you expose some charge to that electric field, of course, yeah, we can find the electric force using this formula at QE. But now, again, since we introduced the electric potential energy, we can calculate it using this expression. QE, it's basically force times position of the charge measured, remember, measured from the negative electrode. So this S is the distance from the negative electrode to the current position of the charge. Great, all right, so we're going to use this. Then, somewhere in the second week of the exam, we introduced Gauss's law. The first equation from the set of Maxwell's equations. So this is true foundation, one of the foundations of electromagnetism, Gauss's law. So if you calculate electric flux over any closed surface, right, and position anywhere in the universe, right, can be used. So if you calculate flux, it should be equal to the total amount of charge inside of the Gaussian surface and divided by the universal constant epsilon naught, right? So most of the time, this law is used to find the electric field, but sometimes you can be interested in the electric flux. Then the problem is quite straightforward. In order to find the electric flux, you just need to count the total amount of charge and divide it by epsilon naught. That's your previous quiz, right? The recent quiz, when most of you actually struggled, you thought it was more complicated. So then, of course, we also played with expression for the electric flux for the simplest possible situation, electric field times dotted with the area vector. Okay, and then after this, we discussed properties of conductors. So let me just quickly remind that. So conductors in the electrostatic equilibrium. In the electrostatic equilibrium, if you wait for a short period of time, conductor exposed to some external electric field usually reaches this electrostatic equilibrium. So at that state, electric field inside of the conductor must be zero, period. We just need to remember that. Then any excess charge can be only on this surface. It's impossible for excess charge to be inside of the conducting material. Right? Then electric field outside must be perpendicular to the surface all the time if it reaches that electrostatic equilibrium. And properties of holes, I decided not to add over here, right? So we will look at the particular example. So in here, after that, we actually introduce these potential energies, and that's pretty much the end of the scope. It's very, very short. So section 25.2, I think, right? So that's the last section for the exam. Right? So electric potential energy. And pretty much that's what you have right now for your homework. Okay, so now let me switch to this part of the whiteboard and let's start discussing problems. So the first problem. Okay, so this problem is lengthy. It's what we did in the very first recitation class. We added two vectors to find net electric force or net electric field. So let's just quickly review that. So it's a problem number 1. And so let me draw a couple of charges. So let's say this is a positive charge. This is negative charge. And we need to find net electric field at this point. At this point P. So the value of the first charge, Q1, minus 6 nanocoulombs, Q2, 3 nanocoulombs. Then some geometry is given. This distance, let's say, be 5 centimeters, and this distance, A. Alright, A is 10 centimeters. Okay, so we need to find the net electric field. E. Alright. Net at point P. Net electric field at point P. So familiar, you remember we solved very, very similar problems. So the steps as a result will be exactly the same, but of course the configuration is different. So first of all, since we're going to find the vector quantity, coordinate system must be shown. How can you deal with vectors, especially components, if you don't show coordinate system? All right, so let me introduce it. I'll position it at the point where we want to find the net electric field. So this will be y, this will be my x. Right. You can position it any point you want, but this is the most convenient since we want to find the electric field at that point. Then, every time I keep encouraging students, draw the picture, it helps you. The graduate students also, and some graduate level courses. So, contribution from the positive charge. What's the direction of the contribution? What's the direction of the electric field created by the second charge? That way, that way, right? So, why I'm asking, because I noticed after the first quiz that some students still not comfortable about the directions of these electric fields created by point charges. So, of course, this way, because electric field lines, they start on positive charges and go to infinity. So, it's one of the electric field lines. I draw the vector, actually, electric field vector. Then, negative charge towards, because electric field lines end on the negative charge. So this will be E1, and this will be E2. Okay, and now graphically we need to find this electric field. So we just need to add these two vectors as vectors, and it's a principle of superposition. That's what we need to find. And you need to have a clear picture. So we are finding the electric field because I noticed that quite often, even till the very end of the semester, some students don't see the difference or big difference between electric field and electric force. Apples and oranges, effectively, right? So electric field, it's something which we use to describe that electrical aura around charged objects. Electric force, it's interactions, right? It's two charges interact with each other, push each other, or attract each other, and we use electric force to describe those interactions. If we had here some charge number 3 at that point, yeah, the question can be find the net electric force acting on that charge from these two charges. But right now, it's just an empty spot. There is nothing over there, just a point in space. And we need to find that contribution, and we need to find the net electric or net electric field at that particular point. So this is nothing, there is nothing, it's just an empty spot. Okay, so, and now the strategy. Find the magnitude of this force, then components. Find the magnitude of that force, which can be done, again, components, after introducing one of the angles. And then once you have two vectors presented in a component form, you just need to add their components in order to find the sum of those two vectors. Right? So exactly the same steps. So let me quickly move through those steps, and I will use my notes. Let me start with this E2 because it's easier. E2, again, it's a magnitude. You see, I didn't put a vector sign on top. It's a magnitude. So, okay. Q, it's a, yeah, E2. So it's absolute value of Q2. And divided by the distance from the charge to the point in question. You can ask why I put an absolute value sign. Because I emphasize a magnitude. Magnitude cannot be negative. Quite often on the exam, I see students use the sign of the charge. As a result, their magnitude becomes negative. No. Magnitude of the vector on the positive number. Right? Of course, we will take care of the direction by looking at the picture when we start writing down components. But this is magnitude. Okay? So, of course, you can plug numbers, except for, remember that B must be in meters. So it's a 5 times 10 to the power of minus 2 meters. And then, of course, it must be squared. Right? I don't want to write the rest of the numbers, but I want to emphasize on that. Guys, if something not clear in terms of my handwriting, just say something quickly, right? So the answer, of course, I will use my notes. And, of course, nano. 10 to the power of negative 9. Don't make those silly mistakes because, again, from time to time I see those. So it will be a 1.079. Okay, I use more sig figs, significantly more. Okay, so now components. Of course, we can write components. E2x and E2y. Y component of this field. What's the y component of the field? 0. Because the whole vector is in the x direction. So we can write immediately 0. And x component, positive or negative? Positive, because the vector and of course component points in the positive x direction. So it will be positive 1.079 times 10 to the power of 4 meters per coulomb. Okay, so let me frame it with green. Preliminary results, not final. Okay, so now, next, let's do the same with vector E1. Yeah, E1. E1 equals to K, absolute value of Q1 divided by R. Okay, yeah, let me write R1 squared. R1, it's a distance from the charge Q1 to the point P. So this is our distance R1. Right? Okay, so of course we can find that R1 easily. R1, okay, Pythagorean theorem, it's a squared plus b squared. Okay, so it will be, squared already, and in terms of meters, so it will be 125, 125 times 10 to the power of minus 4 meters squared. I immediately convert into meters after squaring. We need r squared at the end anyway. Okay, so now, again, I will skip plugging numbers. It will be 0.431 times 10 to the power of 4 newtons per coulomb. Right. Very, very similar steps. Okay, so now that is the magnitude of this vector. So now we need to find components, and in order to do that, we need to introduce one of the angles, either this angle or that. It doesn't matter which one you want to use. In my notes, I think I used this one, theta. Right. Okay, so now tangent theta will be equal. Properties of a right triangle. Guys, if you don't remember or forgot on the exam, again, on the formula sheet at the very end, there is a small triangle in written. So sine, it's a ratio of this versus this. Opposite versus hypotenuse. Cosine, it's adjacent side versus hypotenuse. So look at that. Because again, it's a kind of big problem among the students, but usually by the mid of the semester, most of the students kind of remember that. So it's tangent. Tangent is opposite versus adjacent. So opposite A, adjacent B. Right. Opposite A, adjacent B. Of which you use centimeters or meters, it doesn't matter since you are taking a ratio. So theta will be equal. Of course, you can take arctangent. So it will be 63.43 degrees. Great. So now we have angle, and now we can write down components. Again, if something not clear, tell me. I just took arctangent of both sides. So E, it's a 1 x, and E 1 y. Yeah, let's start with x component. So E1 times which function, cosine or sine, must be used in order to find x component?
Cosine.
Guys, be careful. Again, if you're not confident, right, somewhere at the end of your notebook, write all those properties, because we use them almost every class, right? Almost every class. Right? Or, and again, on the exam, look at the formula sheet. So since x component, it's this, right? So it's adjacent to the chosen angle theta. So cosine function must be used, right? Cosine function must be used. E1 times cosine theta. Sine, positive or negative?
Negative.
Negative, right, exactly. Because you see, this component of this electric field points in the negative x direction. So, since we use convenient angle but not conventional, we have to take care of the pluses and minuses manually. So, minus. That was one of the major points in the first recitation class. At least in my recitation classes, I bugged by them properly. So, of course, you can plug all the numbers and calculate. I will skip, of course, that, and I will write the answer. 0.192 times 10 to the power of 4 newtons per coulomb. So, and now something similar with y component. E1, of course, now there must be sine function. If we use cosine in the previous case, now there must be sine function. And positive or negative component?
Negative.
Of course negative, because this component is also pointing in the negative y direction, so minus. And the after crunching numbers, you will get minus 0.385 times 10 to the power of 4 newtons per coulomb. Okay, so now we found components. So that is the second set of components. And now the last step, principle of superposition, universal principle of superposition. So let me probably, that was my bullet number 1. This is the second bullet, and now this third principle of superposition. So corresponding components must be added. What can be easier than that? So x component and x, y component is easier because this is the 0. So ex equals to e1x plus e2x, negative, positive. Okay, I will look at my notes. So it will be 0.887 times 10 to the power of 4 newtons per coulomb. As for significant figures on the exam, I'm not, okay, we are not that picky. But of course, if you will write, I don't know, 10 digits after the decimal point, when only 3 sig figs are given in the problem, it's kind of not cool, right? So we need to keep a reasonable number of sig figs. Or if the problem is given with, I know, 2, 3 sig figs, and you will round it everything to 1 sig fig, it's also kind of. Even in that case, I tend not to subtract any significant number. Just be reasonable. Be reasonable. It's not like mastering physics, of course, wants to see exactly what it wants to see because it's a piece of software. So E sub y, of course, here this I can do calculations also, since this is 0. So it will be this. Okay, so components. Of course, at this stage, once you found components of a vector, you can say problem is solved, right? So, but sometimes, of course, we can ask for more. What about the magnitude of this vector, or what about the direction? So let's just quickly find that. So magnitude. Of course, it will be Pythagorean theorem effect, essentially, right? So what this is our x component, Ex, and this is our y component, right? So we found this, we found that, so pretty much just a properties of right triangle, Pythagorean theorem. That's what we need to use in order to find the magnitude of this electric field, net electric field, Ex squared plus Ey squared. And of course, I will look at my notes. The answer will be 0.967 times 10 to the power of 4 newtons per coulomb. And so now we can also ask about a direction. So in order to describe direction, usually relative to the x-axis. Because it's, in this case, the most convenient. All right, so let's introduce phi. Of course, you must use a different symbol. Theta has been used over there, so this must be phi or something else. So, tangent, so now direction. Tangent of phi. Opposite side of this triangle, so which is the y component, absolute value of the y component, which is adjacent side, which is absolute value of the x component. E sub y divided by absolute value of E sub x. Again, you can take arctangent or inverse tangent. Of course, you will get phi. Okay, and that will be 23.46. Phi equals to 23.46 degrees. And actually, I'm surprised that I left my answer in this form in my notes. Actually, right now I'm kind of surprised to see that because, of course, you understand I need to add some additional description of this angle, right? Because it's in the fourth quarter. If I leave the answer like this, it means that my vector is in the first quarter, but in our case, it's the fourth one. So I will write below plus x. Oh, clockwise from plus x. Right, so it's very similar to what we did in our first and second recitation class. And the goal is just to review vector algebra because we're going to find components throughout the whole semester. It's 50% of quantities or even more, they're vector quantities. Okay, so then the next problem is very similar, but about finding electric force. Of course, I will skip it, so you can look it by yourself if you want to practice it. Nothing fancy, a little bit boring, straightforward, lengthy, right? But quite often I give a problem like this recently, right? Just to check if you are comfortable. Okay, any questions or any comments or? Okay, yeah. Wait, yeah. Are you just talking among each other?
Wait,
Yeah,
can you, what is the last step? What did you do?
it's a direct. Okay, so we decided to use this angle to describe direction of this vector which we found.
Oh.
Yeah.
Okay.
And what is this? E sub x and E sub y. It's a component of this vector, so this vector. So you see, I projected, and this is my x component, and this is my y component. Values are given. So pretty much now look at this triangle, right triangle, because this is 90 degrees angle. So just the properties of a right triangle. If you want to find this angle, so you can use tangent of angle. It will be opposite side versus adjacent side. Opposite side, it's E sub y, absolute value adjacent, E sub x. Right? Makes sense?
Thank you.
Yeah. Great. Now, something new. Just before the exam, I decided to offer this problem. I'm thinking, should I? You know, I will probably be able to squeeze it into this part of the way. Separate. So, problem number 2. Let's assume that we have 2-point charges given, for Q and Q. Then there is a charge number 3. Everything is along the same line, so pretty much we have 2 charges, right? So they lie on this line, and now I want to find a spot for the charge number 3, where I can position it so that the net force acting on the charge number 3 will be 0. Basically, equilibrium point. Should I position it outside of these 2 charges? Should I position it inside? Or should I position that charge outside on this side? And of course, I actually need to find the exact position, exact point for the charge number 3. So that's the problem. Right. So now, I will probably start with the picture. So that is my x. Okay, line along which our charges are going to be. Alright, so this will be a big one, which, okay, let me label it 1. It's a charge number 1, and the value is for Q. Then charge number 2. And these two, charge number 1 and this charge number 2, this one, let me label it, position it here. So it's a charge number 2. They are fixed. They're stationary. Maybe they want to go, but we nailed them, so they cannot move. Right? So it's a, again, as experimentalist, you can easily arrange that. So charge number 2, and the distance between these 2 charges is L. So okay, L small. Does it look like L? To some extent. Okay, I got too close to the okay, L. And so where should we position Q, the third charge, so that net force equals to 0? Oh, question mark. So that this third charge will be in the equilibrium, right? Static equilibrium. Right? Okay, so now let me check if I mentioned everything. Yeah. So now we can start discussing. So first of all, good, clear. In which region this situation is possible? Is it possible if I position our charge Q over here? Is it possible to have static equilibrium? Why not? we assume that they're all positively charged, right? Yeah, I'm just trying to help you, right? So plus, plus, and this is also plus.
That would be +5 here. It wouldn't like equal each other out in a way.
Both forces are going to point in the same direction. So it means that cancellation of them is impossible, right? So because this is positive, of course this charge is going to repel this charge. So let me label it as E1. Wait, E1, right? So it's a force exerted by this charge. This charge is also positive. Of course it also, wait, I said E1, I said force and I wrote electric field. Sorry, it's Friday. F1. Usually I blame days of the week only. Alright, then these exactly the same. It is going to repel. So electric force is going to be also that way, F2. So both forces in the same direction. Pretty much it doesn't matter where you position this charge, here, 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 all the way to that infinity. So all the time forces are going to be in the same direction. So cancellation is impossible. So this region, so electric force, net force is not equals to 0. There, impossible. Now let's run exactly the same analysis over here in this part, from this point to that infinity. So if you imagine positioning charge, our charge plus Q over here, the story is effectively, essentially the same, right? But of course now forces are going to point that way, to my left, to your right. So this will be, wrong color. So this will be F1, again, repelled by this charge, and also it will be repelled by this charge, both of them, since all of them are positive. Right. Okay, so it means that the same conclusions here, net force is not equals to 0. So it means that there is only one region left between. Right. So now let's position at some arbitrary point Q, which we need to find. So basically, we are going to introduce an unknown, a variable essentially, right? So let's assume that it is at the distance x. So let's say this is x from this charge to the point which we want to find. X is unknown. Then of course, since the total distance between charges is L, so it means that this distance is L minus x. Make sense? X and L minus x. And now, of course, we have Coulomb's law, which describes interaction. So now we just need to write expression for the forces. So, but first let me draw vectors. So, charge number 1 is going to repel this charge. So this will be force F1. This charge also is going to repel that charge, but of course in the opposite direction. F2, right? So opposite directions, cancellations are possible. Yeah.
We're like placing the charge so that the force on the placed charge is.
Say it again.
So we're placing the charge Q in a way in a position so that the force on the charge Q itself doesn't place it zero, right?
So pretty much, I'm imagining that at this point there will be cancellation. So and x is unknown. So pretty much now, using this situation, I'm going to write the equation, and from that equation, I should be able to extract this x, which is unknown. Right. So basically, that's the philosophy of the problem. Okay. So now F1 must be equal to F2 at that point. So I can write, so since we want to find this, I mean, satisfy that, so it means that F1 absolute value must be equal to F2. Point charges, so of course we can use Coulomb's law. So I can write K. F1, it's a this and that charge, so it will be 4Q times Q divided by X to the power of 2. Coulomb's law, force F1, right? K, Q, q over r squared, but in this case r is x. So now we need to write exactly the same for F2, but now for these two charges. Okay, not exactly the same, similar. So it will be K. Charges Q and Q, charges are the same, right? And now the distance between these two charges, L minus x squared, of course. Great, so that's the equation. That's the physics. Now, of course, we can cancel K. Q and Q squared, and here Q squared can be also cancelled. So now after cancellation, we're going to get 1 over x squared equals to, oh no, not 1, sorry, 4. 4 over x squared and 1 over L minus x to the power of 2. I just first canceled all constants, right? K and Q squared. Now let's just write it in a better way. So it will be 4L minus x to the power of 2 equals x to the power of 2. I just multiplied this and that, this and this, basically proportions. Then, actually nice numbers. If I take a square root of both sides, on purpose of course I pick those numbers, so I can take a square root nicely. Right. So I can take square root of this side, square root of that side, and we will get 2L minus x equals 2x. We're nailing it almost, getting closer to the end. Right? So now, let me move all x's to one side, so it will be x plus 2x. This is 2L equals x plus 2x. So 2L minus 2x. So minus 2x goes to that side with plus. So 3x. So 3x equals 2L. And of course, as a result, we're getting the answer. X equals 2. 2/3 of an L. It's a nice problem. Not complicated, but at the same time, to some extent, I would say elegant. So you need to apply some logic, conceptual understanding. Yeah.
So if you ask us on the exam, and so we can't just say if we point charge goes here to cancel out, you want us to prove everything. Prove why we cancel out.
Why you canceling out? You mean mathematical?
Right, yeah. You would want us to write everything out. Why not just say it would cancel out here? Because
Okay, you're talking about cancellation. Canceling these two forces, or here mathematical manipulations.
I'm just saying on the exam, the question was where should we position, and then so the position is here. You want us to prove that position is.
Oh, okay. Of course, for the question like this, I would expect something. You would, in words or somehow explain why this is impossible, why that is impossible in that region, and then so it looks like in this region it is possible, and then I expect that you would show the physics, right? And no, you're just holding your hand just now. Yeah.
So we're trying to find the net electric force to be 0 at Q3, right?
A net electric force equals 0 on Q3. Yeah, on the third charge. Yeah. Charges 1 and 2 are fixed, stationary, right? We can arrange it as an experimental. Okay, now I can start erasing this. So that was number 2. Now number 3. I think, these are somewhat conceptual. Let me also discuss that. Because again, based on the quiz results, quiz 1, I realized that not everyone is comfortable with finding directions of the net directions of the electric field, and of course net electric field. So 3. All right. So let's assume that we have. You know what? First, let me draw geometry, and then I will show the electrical part. So let's say we have 2 squares. Okay, listen. So, 1 square, the second square, so all the distances are the same. And now let me position a couple of charges. One is at this point, let's say it's positively charged, plus Q. And the second one is negatively charged over here, minus. So it's minus Q. And I just want to find the net electric field at some of those points. Because again, I was grading quiz number 1 and I was surprised that some students still. So, in order to answer this question, you need to remember every time that positive charges, electric field lines, are like that. And if you have a negative charge, electric field lines are these. So every time you need to imagine where is your point relative to this or that charge. See what's the direction of the electric field. So let's start with point, I don't know, this point. No, which one? Which one? This corner, for example. So net electric field. Of course, superposition of 2 electric fields. Contribution from the negative charge to the net electric field at this point. So effectively, we're talking about this point. This is the point relative to our negative charge. So it means that electric field is straight up towards the negative charge. So this, you know what, let me label this is 1, charge number 1, and this is charge number 2. So this will be E sub 2. Then, charge number 1, it's a positive charge, so effectively we're talking about point, this is our point. So of course electric field is going to be this way. Right? So this is our point, and electric field along this line. So this is E1. And principle of superposition. So this will be net electric field at that point. Basically, it's an alphabet foundation, right? I was surprised that after the first quiz, so I decided to add these questions. Then, for example, let's say at this point, similar positive charge. Effectively, we're talking about this is the position of our point relative to our positive charge. So electric field is straight up. Right? Then, negative charge. This point relative to the negative charge, we're talking about, this is the point, our point, right? Relative to the negative charge. So electric field is towards, so along this line. So this is E2. And principle of superposition. What else? Let's find, for example, at this point, the last piece. Very similar, again, positive charge. This point relative to the point charge, it's a point is here, so electric field straight down. So E1. Then negative charge. So this point relative to the negative charge, it's this one. Right? So it means that it's towards that negative charge. So let me draw this dashed line. So this will be E sub 2. So again, it's close superposition. Lots of red. Now, let's increase the number of charges. Because yeah, questions like this quite often I give on the first midterm exam just to check your ability to show the directions of the electric field. Okay, any questions of this? Yeah, it's a foundation. All right, so now let me look at this situation. I will draw it here below. Again, a square. Because of the symmetry, it's nice to use square. Okay, good enough. And now let me position charges at each corner of this square. Let me start with the positive, and the rest are going to be negative. So this is positive charge plus Q. They are of the same absolute value. So Q, then minus Q, then minus Q, and minus Q. And we're interested in the net electric field at the center, I think. Yeah, at the center. So let me draw these diagonal lines. So E at the center. So basically the same idea. We just need to draw all contributions to the net electric field at the point in question. So let me start, of course, with the positive charge. It's at this point, so of course it is away from the positive charge. Away. So it will be this electric field. You know what? Let me label them. So it's a charge 1, which we label. This will be my charge 2. This is 3, and this is 4. So as a result, this is E1. Then, contribution from this, okay, charge 2, towards the negative charge. So this will be, alright, wait. Good. Alright, so E sub 2. Then, contribution from the charge 4, again, towards the charge 4. Because again, it's effectively, it's this point towards. So E4. And in absolute value, this charge and that charge are the same. Oh, not charge, electric field. The same, right? And so the last contribution from the charge number 3, it will be again towards the negative charge. So relative to this charge, it's we're talking about this point. So I can draw it here. So E3. So what's the direction of the net electric field?
Going from 1 to 3.
Yeah, these contributions, they are not nice towards each other. Right? They cancel each other. And these two, of course, in the same direction. So they're going to add each other, giving us a reasonably strong electric field along this diagonal line. So it will be, okay, let me use green for the net. So this will be E net. So that's how it should be analyzed. Sometimes some contributions can cancel each other. As I said, quite often among multiple choice questions, I give questions like this. They don't require a significant amount of time.
So in the answer box, would you just put E1 or E1 plus E3?
In the answer box, it depends what's the question,
Oh.
how I state the
Yeah, yeah.
question, right? So I can ask, so show me on the picture, right? So right now I haven't created the exam yet, so I cannot say. Yeah.
Okay. If on the exam it asks for like the magnitude of, if it just asks for the number, right? What would it be? Would it be
Magnitude, for the question like this, I don't think that I would ask for a magnitude. I just want to see your ability to draw vectors with the right directions, analyze the situation, if vectors are canceling each other or not. It's conceptual. Okay, enough of these charges, point charges. Now, Gauss's law. Let's discuss Gauss's law. Yeah, let me erase this. So usually the exam review session is about slightly less than 3 hours. 2 hours, 45 minutes. So number 4. Gauss's law. So now it's a Gauss's law. And I promised from the very beginning that there will be definitely a problem about Gauss's law. It's either spherical symmetry or cylindrical symmetry. We only discussed those two types of symmetry. All right, so here I prepared spherical. Okay, now I need to apply my best ability to draw circles. Okay, not bad. All right, so now second, it's more complicated now. Okay. Every time I was looking online for some tools which can be used. Okay, good enough. It's not going to be any better. Non-conducting material. Yeah, let me highlight it like this. So we have a non-conducting sphere with a with cavity, with a spherical cavity. Radii, let's say this is B, this is A, and you know, in the problem, at the center there is a point charge, but I decided just now, let me position another non-conducting disk of radius, I don't know, C. Again, at the center, there is a non-conducting sphere at the center. Non-conducting, it means that all these properties cannot be used here. And charges. So let's assume that shell is charged with plus Q. Yeah. So this has a charge plus Q. And this sphere is charged with plus Q small. Okay, so what we need to find? Electric field inside of this non-conducting sphere with the hole. Of course, the question can be asked about finding electric field outside or over here or inside of that, but I pick the most complicated. Okay, find the electric field when R is between A small and B small. in that region. So, first step. Yeah, of course, you can use either Coulomb's law, but Coulomb's law application over here in integration, it will be not pleasant. So, definitely Gauss's law. Definitely Gauss's law should be used. E dot dA equals to Q enclosed over epsilon naught. What is the first step we have to make before we can start applying Gauss's law?
Identifying the surface.
Gaussian surface. We have to make a decision about the Gaussian surface because without that decision, integration over that surface, you have to make the decision. Charge enclosed, again, within that surface. So you have to make that decision. And guys, careful, because quite often on the exam, I usually walk around and I see, I ask the question about finding electric field in one region, but students draw a Gaussian surface in a different region. So be careful, because it's a silly mistake, but usually I'm aware of that. I usually walk around and announce, guys, look which region you need to find, in which region you need to find the electric field, right? Because yeah, it's a unnecessary mistake. All right. Okay, so since we're interested in the electric field over here, of course, I will pick my Gaussian surface in that region of some arbitrary radius r. So that's my Gaussian surface. So let me show it. Gaussian surface. Okay, and now steps are very, very similar to what we did in the lecture. So I will start with, of course, first with the flux. All right, so integral of E dot dA. And in the future, when we will introduce Ampere's law, steps will be very similar when we're going to evaluate those integral in the future. So you're going to see these steps quite often. Okay, so first, directions of the electric field and directions of area vector. Usually I ask that, I want to see them. So if you pick, let's say I pick this patch, dA. So area vector, you remember, must be towards the outward, point outward. It's by convention for the Gauss's law. So this is dA. Of course I can draw it even here, for example, if I want, but one is enough. Then electric field, I justified in the lecture that the electric field will be definitely radial. Here, of course, I don't ask for any justifications. If you just show direction of the correct direction of the electric field, it will be more than enough. So radial electric field. Usually books say that because of the symmetry, it's obvious that the electric field is going to be radial. Oh, over here. Okay, enough of these vectors. And now, of course, I can open my explanation box. Since electric field is parallel to dA, of course, I can take care of that dot product. I can write explicitly E dot dA equals to E dA times cosine of angle between two parallel vectors. 0. 0 degrees. So of course, cosine of 0 degrees is 1, so it's an EDA. So now we have magnitudes of these two vectors. Here we have vectors, now we have magnitudes. So it's an achievement of the first step. We managed to remove vectors from our game. Now it's just the magnitudes, absolute values. And so now the next step, using again the symmetry. So if you look from this point, the distribution of charges, and it will be exactly the same if you look at the distribution of charges from for example, from this patch. So it means that electric field strength over there, or electric field strength over here, or there, or any other point on the Gaussian surface must be exactly the same, is exactly the same, because of the symmetry. So I can write, so since E is constant, sometimes I see students write electric field is uniform. No, it's not uniform in this case. Because if you step away from the Gaussian surface, electric field will have a different value. If you step away, if you step farther away, electric field will go smaller, become smaller. If you move closer, electric field gets stronger. It just happens because of the symmetry. Electric field is constant on the Gaussian surface. It's not uniform. Of course, I would never subtract any points for that statement, but it's not right. Constant on the Gaussian surface. So, if it's constant, of course, any constant factor can be extracted from the sign of integration. Right. So, as a result, we have electric field and integral of dA. Again, it's a calculus 3, this integral. It's still not trivial, but we know the answer. We know the answer. It's the area of the Gaussian surface, which is, again, those formulas are in the formula sheet. Closer to the end of the formula sheet are given area of the sphere, volume of the sphere, area of the circle, area of the disk, whatever. Right? So, because quite often I see students write just wrong formulas, and we shouldn't be making mistakes of these formulas. So, 4 pi r squared, small r. Okay, so our value of the flux, E times 4 pi r squared, charged right now. Okay, and so according to the Gauss's law, it must be equal to Q enclosed over epsilon naught. And now the fun part, finding the amount of charge within the Gaussian surface. That's where, I know, 70% of mistakes, 70% of students at least making mistake at this part of the problem. So, in everything that we need to remember, it's a sort of definition of Q enclosed. It's all charge physically present. Where it's present within the Gaussian surface, Gauss's law doesn't care. If it is inside, we just need to count it in. And the second, of course, we need to remember the definition of volume charge density, Q divided by P. Okay, this is my rule. So that fact and this, that's what we need to know in order to answer, in order to find this Q enclosed. Yeah, and another thing which usually I emphasize on that, and every semester students make that mistake. Usually at this point I ask, so what's Q enclosed? Okay, students, see Q enclosed over here, let me solve it for Q enclosed in terms of E. You're writing unknown in terms of another unknown. It's not wrong, it just doesn't give you any, it's not useful. It's not useful. It's useless actually, right? Of course, basically, and they claim, okay, it's Q enclosed. Basically means that 0 points will be given for that because, again, it's not wrong, it's useless. So, Q enclosed. So let's start counting where those charges are. Let's start from the very center. First contribution, first amount of first charge. What? Q, small, right? Yeah, because that, not disk, it's a sphere. At the very center, this sphere is totally, completely inside of the Gaussian surface. So of course this charge is somehow distributed over that sphere, but we don't care where the charge is as long as it is inside of the Gaussian surface, we need to count it in. So this Q small goes immediately. First charge, Q. In my notes, actually, instead of this sphere, I just put a point charge Q, but it's not going to change my solution for the electric field in this region. It doesn't matter if it's a point charge or something more complicated. If you see the charge completely inside, just write it in, Q small. But of course it's the first part, so Q, it's this one. Okay, maybe I can even show that this charge comes. Then, second part, of course, in this region between sphere with radius A and sphere with radius r small. That part, that charge also is inside. Let me highlight it with blue. So, and then this region. Right? Inside? Inside. So we need to count that only. because this contribution must go over here. That part. So, how can we find that amount of charge?
We find the volume of that part.
Yes.
Multiplied with the density.
So, now, in order to answer this question, it's all here. So, nothing else. We just need to remember the definition of the volume charge density. So, we need to add, so again, it's a charge. You can use any charge divided by the volume over which that particular charge is distributed. Right? So now, if we are interested in this amount of charge, I mean in this volume, this amount of charge, if we are interested, so we need to do what? Q equals rho, we need to find rho somehow, and multiply by the volume over which this charge is distributed. So this volume, that's what you just told me, right? So volume charge density multiplied by this volume. So let's do that. First step, so it will be rho times volume. And how can I label that volume? It's between A and R, small. So let me write something like A and R. Subscript A, R. So between those spheres with those radii. So how can we find that volume? Now it's geometry. So we need to find the volume of the sphere with a concentric hole. Concentric spherical hole. Right? So it means that you need to take the volume of the larger sphere and subtract the volume of the hole. We've done it in the recitation classes, I think. So let me show it like this. So it's a volume of the sphere with radius r small minus volume of the sphere with radius a. And now let me show it graphically. So effectively, in order to find volume this, we need to take volume of the sphere without hole and subtract volume of the hole. Can you see it? I try to find the button how to reduce the height of this table, but I can't find it. Where is it? I think at some point, it's here. It's nice. I also have it. I told you. So now it's good. So this is our volume. So volume with the of the sphere with radius r small minus volume of the sphere with a small. Right? See that? Yeah, it's a simple geometry. And of course we can write it again. Formula in the formula sheet. It's a 4 pi r to the power of 3 divided by 3 r to the power of 3. Volume of the sphere. So it's a 4 pi over 3 r to the power of 3 minus 4 pi over 3 a to the power of 3. So that's our volume. Now, density. Again, back to the definition of the density. But now we need to use different charge in order to find charge density. What? We know that this charge plus Q is uniformly distributed over this object with between a sphere with radius B and sphere with radius A. Right? Okay, so now rho equals to total charge Q, that positive, divided by the volume between spheres with radius B and sphere and the hole. So exactly the same idea. We need to take now V sub B minus V sub A. You know what, I feel like I should have started over here so I have enough room in order to finish this line. Okay, let me, it's not wrong, it's right. B and A, right? Yeah. So Q divided by volume of this sphere with radius B minus volume of the sphere with radius A. It's a geometry and the definition of the volume charge density, nothing else in this part. So it will be Q divided by 4 pi over 3 b to the power 3 minus a to the power 3. So this goes into that. So now we just need to combine these two expressions, and that will be the answer. Clear? Ah, okay. I see you. You just were showing the thumbs up, right? Okay. Again, this stuff, it's a high school stuff, even middle school stuff, right? So, I'm not trying to insult you, right? That's where we were trained, right? When I was in your shoes, right? Yeah.
So the Q in the volume charge density, is that Q outer?
Q volume charge over here.
Yeah.
So every time you just need to remember whatever charge you use. So if you use Q capital, okay, this one. So you need to divide it by the volume over which that particular charge is distributed. You need to remember these magic words: charge divided by the volume over which that charge is distributed. Over here we use what? Q this charge. So we took volume charge density out of this formula. So volume charge density multiplied by the volume over which this charge is distributed.
So is that Q on the surface or inside?
What charge is surface
In
inside?
the red.
We have only two charges, this Q small, Q capital.
Yeah, Q capital.
Q capital, so over here, the Q small is not involved. Only over here, Q small.
But where does that capital Q act
I mean, this one?
on? Yeah, the one.
No, this is just a definition. Definition.
The one in the red, the Q capital. In the diagram. Yeah, where does that act?
Okay, this is over here. It's a discharge. We find that we use the charge in order to find volume charge density. This is given. This is given. So I need to use that in order to find volume charge density.
Okay, that's
Okay, let me put it all together. All right, so Q small plus Q capital over 4 pi over 3 b to the power 3 minus a to the power 3. So it's a density. And multiply it now by this volume. So which is again 4 pi over 3 can be factored out. And I to the power 3 minus a to the power 3. Wait, no. That bracket, that parenthesis is not, shouldn't be there. Alright, so 4 pi over 3 can be cancelled. And as a result, we will have the final expression. So it's a Q small plus Q capital, and the ratio of these R cubed, A cubed, then B cubed minus A. So you see, we just subtracted the whole all the time. Upstairs, downstairs. So this amount, this is the Q enclosed. And it's about, I give you the quiz number 4, take home quiz, it's about all this, right? So in order to find, how to find this charge density, that charge density, how to find the amount of charge in that part of the object, this part of the object. It's not rocket science, it's some very, very basic ideas, right? And again, it's a mass density, exactly the same ideas with the mass densities, right? I can replace charge with the word mass, and exactly the same logic must be applied. Oh, I know, maybe, mass, a charge. I tried to find another example, but cannot think of anything else. Because in our life we have masses and charges all the time. Okay, so now we just need to go back, plug Q enclosed, and finish the problem. So now, and you know what, I will continue over here because I'm kind of running out of space, so I will plug now this Q enclosed into our Gauss law. So, E times 4 pi r to the power of 2 equals to 1 over epsilon naught, and our ugly expression r to the power of 3 minus 8 minus 8. And now get the solution. Okay, so and our unknown is over here. So we just need to move this 4 pi r squared to that side and problem is solved. And so E as a function of r will be equal. So Q plus Q capital R minus 8 divided by and divided by 4 pi epsilon naught and r to the power of 2. And again, that's would be region between R between A and B. This finding charge density is barely a physics. It's a just definition of charge density and geometry. That's it. Let me ask you another quick question. What if we want to find the electric field just outside? Of course, these steps up to this point are going to be exactly the same. But what will be Q enclosed in that case if we want to find the electric field over here? What will be the amount of charge enclosed in this case? You should be able to answer it like that. So, because again, you remember, where the charge is positioned, Gauss's law doesn't care as long as it is inside of the Gaussian surface. Q small, inside? Of course the whole thing is inside, so Q small. Then, what about Q capital? Now, the whole Q capital is also inside. It will be just Q small plus Q capital, without all these crazy manipulations. Outside, it will be like that solution. But of course, I didn't want to discuss something which is trivial. Right? I need to scare you before the exam. No, just not scare, but of course, it's better to discuss something more complicated. Yeah. Yeah. Okay. I'm on the way. Right. I'm not transparent. Right? I try to remember that, but I thought you already have finished writing it. So let me check what this thing is doing. Yeah, it's charging. It just doesn't show up. Okay, so now let's discuss flux, electric flux, conceptual questions. Difficult to find problems about flux, which are complicated. Yeah, it's possible. So, can I start erasing it? Okay, great. All right, flux. So it will be conceptual questions. Number 5. Wait. Flux with English L. So let's say part A. What if we have this situation? We have some closed surface. I know this cylinder. And let's say there is a charge over here, plus Q. And simple question, conceptual. What's the amount? What's the total electric flux through this closed surface? Number of electric field lines crossing through this surface. What's the electric flux?
0.
0. It's basically your quiz number 3, right? So which you had like a few days ago, right? So in order to answer that question, you remember what is the meaning of the Gauss's law? So that's the Gauss's law. And what's the meaning of the left-hand side of that Gauss's law? It's the electric flux. Electric flux. So pretty much, if the question is about electric flux, flux equals to total amount of charge inside of the Gauss, inside of your surface, whatever your surface you want to discuss, or given in the problem, divided by that constant epsilon naught. That's it. Finding electric field, yeah, you saw how much time we spent. But finding electric flux, it's way easier. Okay, so in this case, Q enclosed equals to 0. So of course, as a result, electric flux is 0. Very simple. Then, part B. So what if we have this situation again, the same cylinder? I don't know, I started liking cylinders. And a few charges. Let me draw. So let's say this is plus Q, this is minus Q, this is what? Again, plus Q. The same question. What's the total flux through our cylindrical surface?
0.
Of course, again, 0. Charges outside, we're not counting. Charges inside, exactly the same, but opposite in sign, right? So in this case, I can write that electric flux, which is Q in over epsilon naught, so it's a plus Q minus Q divided by epsilon naught, so it is equal to 0. I don't know. Yeah, I can add more charges or reduce, but the idea is exactly the same. So now let me increase complexity of this, and it's A, B, and now C, with some calculations. Again, the cylinder. Let me draw it like this. So the cylinder. Charges. 2 charges are inside. So it's almost like a Halloween mask. No, seriously, right? Oh no, it looks like a KKK mask. Sorry. I need to delete that from my video. 5K minus 5K, and but it does remind some spooky stuff. Plus 2Q. Right. And so, what is given? Actually, it was from one of the exams, and it was among multiple choice questions. I took it. So, we know the flux through, so first of all, 3 surfaces we can identify, right? The top, bottom, and the side. So cylinder consists of 3 parts. So let me write. So it's a top, of course this is bottom, and the side surface. So what is given? We know that the flux through the top is given. Minus 15 newtons times meters squared over coulombs. Then we also know the flux through this side. Flux through the side is cylindrical wall. This cylindrical wall is 10 newtons times meters squared over coulombs. And the question is, what's the value of amount of flux through the bottom, I think, right? Yeah. So we need to find flux through the bottom. So this is slightly more complicated. But anyway, so how can we write? Let me separate it like this. So how can we write the total flux through the whole cylinder? Of course, we can divide it into three parts, right? Total flux. It's a flux through the top, through the bottom, plus through the side. Flux through the top, plus flux through the bottom, and plus flux through the cylindrical side. And so what's the total value of the total flux?
Q n over epsilon naught.
And what is Q?
0.
So the total flux is
0.
0. So using this previously discussed stuff, we can tell immediately the total flux. So flux total equals to again Q enclosed over epsilon naught, and Q enclosed is plus 5 coulombs minus 5 coulombs divided by epsilon naught, so it's 0. So this is 0. And now this is 0, this is given, that needs to be found. So it's not complicated, not that complicated. So from here we can, let me continue over here. So it will be flux through the bottom. Will be equal to what? Minus flux through the top, minus flux through the side. So now I just need to add two numbers. So this is negative, so it will be minus 15. Okay, I will skip units. They're too big. I mean, too complicated, right? So minus and minus from the expression, and minus because the value of the flux is negative. And then flux through the side is actually negative, so it will be minus 10. So it will be equal to positive 5. So, and now, of course, I will write units. And let me check if I can crunch my numbers. Yeah, correct. That's correct. So it was on one of the exams among multiple choice questions. Yeah.
So when you say the side, you mean like the cylindrical wall?
Yeah, cylindrical wall. Yeah, any cylinder you can split into three parts. Okay, enough of the flux. So now, it's only 1 hour 40 minutes, so it's not that bad. The record was on the final exam 4.5 hours or something. It was final exam, sorry. Don't. Yeah, usually after that I'm really exhausted. Right, but I'm trying to keep around 4 hours. It's not easy. All right. Now, okay. Can I erase this? Okay, so now let's discuss quickly properties of conductors. It's something similar to the quiz. And then a couple of problems about one, motion of the charges in the uniform electric field using energy approach and force approach. And after that, we will call it a day. So that will be number 6. So, conductor. Actually, just now I saw the emitter. He came from the Physics 1 exam review session. 3 hours. So he said Dr. Joseph covered the first hour, and then Dr. Midler covered the other 2 hours. It's normal. All right. So let's assume that this is my conductor. Sometimes just for fun, I try to draw them in some funny shape. I don't know, in the shape of a Mickey Mouse or something. in the graduate level classical mechanics, I sort of draw Mickey Mouse out of some spheres, right, and ask to find the center of mass using some trick. And I just bring some fun. If you go physics fun, if you can find any fun in physics. All right. Okay. So now let's assume that we have these 2 holes in our conductor. So conducting material is there. So that's conductor. Then, bless you, right? So conductor is charged. So let me show that Q total is minus 6 coulombs. Then now let me dump a few charges in these holes. Right, so let's say over here we have minus 2 coulombs. Then inside of this sphere we have plus 8 coulombs and then minus 3 coulombs. Yeah. So we need to find, actually you can guess the questions, right? So we need to find the amount of charge on this inner surface number 1, inner surface number 2, and outer surface the only one. So let me write. So we need to find QE1, QI2, I stands for inner, and Q out. Which way I label it? I don't remember. Just out. It's so very similar to what you did in your quiz number 3 this week. I just increase number of holes. I can add 3 holes. I can create 3 holes, 5 holes, right? So, but the idea will be exactly the same. Yeah.
Which one is hole 1 and which one is 2?
Say it louder.
Which one is 1 and which one is 2?
Yeah. Now I would start saying that. Right? So let's say this is number 1 and this is number 2. So this will be QI1, and over here there will be QI2. Okay, so the amount of charge on the inner surface number 1. Nothing to discuss. The answer. Of course, plus 2 coulombs, right? Exactly the same amount of charge as inside, but opposite inside. Right? So basically, we can say this charge, positive charge, is induced on the inner surface. Is induced. So the electrons inside of the conductor, there are tons of them. They are free, right? And so they see this negative charge, they hate it. You remember all the negative charges, they don't like each other, they want to run away from each other, the same positive charges. So it means that electrons are going to run away from this surface, leaving behind positively charged surface. Right? Because again, you remember in the conductors, positive charges, they don't move. They are part of the crystalline structure. Electrons, they can come closer, making surface positive, or they can run away, making surface positively charged, right? That's how it works. So it means that over here, we're going to have positive charge plus plus. Of course, distribution can be complicated. I don't want to discuss that. But we can say about the total amount of charge induced on the inner surface. It will be exactly the same as the charge inside, but opposite inside. So Q in, QI1 is plus 2. Again, if you want to prove it, use Gauss's law like we did in the lecture. But usually I don't demand the proof. If you just write down the correct answer, I will buy it. Then, QI2. So, the net charge inside will be what? Plus 8 minus 3, it will be plus 5. So it means that the negative charge will be induced. Minus 5 coulombs will be induced on the inner surface of the second pole. So it will be equal to minus 8 coulombs minus 3 coulombs. So it will be minus 5 coulombs. So negative charge, so electrons will actually run to the inner surface. So over here we're going to have negative charges. Okay, so and now the last step, find the amount of charge on the outer surface. Conservation of charge inside of the conducting material. Only charges inside of the conducting material. Right? So now, conservation of charge inside of our conductor. So Q total, and plus we know. It's again like I compare it with that situation of 2 rooms and 10 people. Here now we have 3 rooms and 10 people, right? So exactly the same idea. So room number 1, outer surface. Room number 2, inner surface this. Room number 3, inner surface that one. So 10 people, if there are 2 people in one room, then there must be 3 and 5 in the other 2 rooms, right? So again, conservation of charge in 3 rooms which are connected. So Q total equals to Q out plus QI1 plus QI2. I add more holes, more terms will be in this equation, right? So that's the only difference. Philosophy idea is exactly the same. Right, so that's our unknown. We found this, we found that. This was given from the very beginning. So we can write, so Q on the outer surface will be equal Q total minus QI1 minus QI2. And again, I told in my recitation class many times, be careful over here with these minuses because quite often students try to skip steps and making really sometimes silly mistakes. Really unnecessary. So Q total, what? Minus 6 coulombs. Then minus from the expression, and QI1 is 2. Then again minus from the expression, right? And QI2 is negative, so minus 5 coulombs. So the simple algebra, I'll try to make no mistakes. So minus 8 plus 5, 3. Wait, do. Minus 8, minus negative 3, right? Where are my notes? Yeah, negative 3. Cool. Good. Again, quite often something like this among multiple choice questions somewhere. Right? No, it's an open question basically. Write down the amount of charge on that surface, on this surface, and so on. So, another thing which sort of conceptual. So let's say we have a sphere conductor, metal. And let me dump some charges, I know, plus Q, I know, minus Q, I know, plus 36Q, right, minus 273Q. You can write any numbers. What's the electric field inside of the conductor? 0. Of course. So those electrons, tons of those electrons inside of the conductor, they will run like crazy first, and then they will distribute themselves somehow around this surface but they will definitely achieve the state where electrostatic equilibrium, electric field inside will be zero. So they will balance out all the electric fields created by the charges outside. Electric field inside of the conductor is zero. Okay. Now, the last two problems about energy approach and force approach to solve problems about motion of charges in some electric field. So, and these problems are usually one of the, I don't want to say favorite, but the least number of mistakes are made by students in the problems like that. So they're quite comfortable. This. Still alive? Yeah. Okay, can I? So, yeah, let's start first with the force approach and then energy approach. So that will be number 7. Okay, so a parallel plate capacitor. E capacitor. So what? Okay, let me draw first the picture. Then. I'm doing better with capacitors than with spheres. So this is positively charged. Right, so of course electric field lines from plus to minus. Right, so E. And what? Actually, numbers are not given. So I'll just write down which quantities are given. No numbers. So minus, 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 minus. Because I notice quite often students are kind of addicted to numbers, right? And sometimes on purpose I don't give numbers. So you would suffer a little bit. Not suffer, just need to be comfortable doing without numbers. So then electron. So let me first write what is given about the capacitor. So total charge on the plate Q, then area of the plates, and the spacing between the plates. So these are given numbers. Values. Then there is an electron. Is it electron? Yeah. So, of course, mass, you can open the book, charge, you remember, and we also know that initial velocity of the electron is 0. So it is released from let's say, from this point, from the negative electron. So V naught equals to 0. Of course, you can tell me immediately what is this electron going to do. Of course, it will be repelled by the negative electrode, attracted by the positive electrode. So it is going to fly to our right. So this way. So this will be our initial point. This will be our final point. Right. And the question is about time. We need to find the travel time. So I think I wrote everything, gave you everything. So we need to find which way I labeled it, just T. Yeah, just T. Travel time, total travel time. And here we're going to use the force approach, basically using forces, Newton's second law, and so on. To be accurate, let me introduce coordinate system. Which way I label it, S or X? X. So the origin, put it on a negative electrode all the time. So that's where we usually position. Then D is there. And so now let's just outline or create a skeleton of the solution. We need to answer the question about the travel time. So what do we usually use in order to find these kinematic quantities, velocities, positions, travel time, acceleration? So which equations do we usually use to find those quantities, kinematic quantities? Usually kinematic equations. Right? So, and the essential part of the kinematic equation is an acceleration. So in this case, we will have to, at this point, we will have to find acceleration and then use one of the kinematic equations. Then, in order to find, or in order to know acceleration, how can we find acceleration? It's either kinematic equations, but we're going to use them later, or Newton's second law. So, Newton's second law, and it means that before finding acceleration, we will have to find the force. In this case, of course, it will be an electric force. And so now the first step, I want to say the last step, the last in this discussion and the first one in the solution, electric field. So that's the skeleton of the solution. So now we just need to carefully go through these steps. Yeah, of course, the expression formula which connects force and the electric field, of course, QE. All right. So now we just need to carefully go through this. And I want to be careful. I want to write everything in a vector form in order to get acceleration. If it's going to be negative, I will get that negative. If it's positive, then it's easier. Okay, so expression, probably I will start here. Let's start with the electric field. E as a vector. Magnitude of the electric field inside of a parallel plate capacitor. Eta over epsilon naught. So eta over epsilon naught. Eta is what? It's a surface charge density. Right, amount of charge per unit area of an electrode. Okay, this electrode, usually positive electrode. And so since I wrote it as a vector, so let me write it as a vector. So direction of the electric field from plus to minus, negative x direction. Negative x direction. You see electric field this way, but x-axis that way. So minus I hat. Unit vector in the positive x direction, I hat. Okay, so now surface charge density. Eta equals definition of surface charge density, total charge divided by the area over which that charge is distributed. Charge is given Q capital, area also given. So by definition, it's a Q divided by A. Circular area can be given sometimes, or square. In this case, just A. So let me plug it. Of course, it will be Q over A times epsilon naught, and in the negative I, in negative x direction. So, yeah, electric field. So we started moving through our skeleton. So next step, we need to write the electric force acting on this electron. So F equals to Q times E. Electron, negatively charged. Let's show that minus explicitly. So let me write it. Minus absolute value of the charge in times electric field. Q over epsilon naught A, and in the minus I hat direction. So I just wrote that minus explicitly. So minus from here, minus from there is going to give us force in the positive x direction. And we knew that. You told me, oh, what I forgot who, from the very beginning that charge is going to move that way, accelerating, so because of that force. So force is in the positive x direction. So it will be absolute value q small times q capital divided by epsilon naught times a, and in the positive I x in the positive direction. So now we are at this stop. Now acceleration, mass is only positive, mass cannot be negative, right? So it's easy. All the time direction of the force and direction of acceleration are the same. So acceleration equals to value of force divided by the mass. So I just need to rewrite that expression with m in the denominator. So it will be q times q capital divided by epsilon naught m a, and in the positive x direction. This is how I crunched one mark holder. I found it so useful, but whenever it took me some time to find one company which actually makes this marker holders. So I'm quite surprised. Okay, anyway, acceleration is positive, right? So actually everything is great. Now, can we use kinematic equations? Is it allowed at this point to use kinematic equations? Why? It's an essential. Every time before we use kinematic equations, every time I stop and ask, guys, justify it, right? Because we have acceleration and velocity. You started with the right word, but you didn't complete it. Oh, he was first, right?
Acceleration has to be constant.
Constant. Only then. Because there are plenty of situations where accelerations are not constant. And if you try to use a kinematic equations, they're just not applicable there. It will be just wrong, right? So so we can use kinematic equations if acceleration is constant. In our case, it is constant. Constant, 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 constant. Everything is constant. So, constant. So, kinematic equations can be used. Okay, so now we're at the final stop. Not the stop, the final transition from the acceleration to. And acceleration is positive, so we will write positive acceleration in our kinematic equations. Okay, which kinematic equation should be the best?
It's the one where like.
So we have three. Let me just remind quickly. First one, let's say, which allows us to predict the future position, equation for x, right? Time is involved. Then second equation, which allows us to predict the future of the velocity, equation for the velocity and time is present. And then equation number 3, it's an equation where time is missing. Basically not missing, we just removed it. We just combined the first two equations, eliminated time, and we introduced what is called a no time equation. In this case, no time equation is not an option for us because we need to find time, right? So we need to find time. So then, can we use the equation for the velocity? No, I agree, because we know initial velocity is 0. Then there is a time which is unknown, which we need to find. And then, do we know the final velocity?
No.
Again, collision, because sometimes students imagine, okay, it is going to collide with the plate, so velocity will be 0. No, we're discussing only the flight. Collision, it's a different physics. That will be different problem if you want to discuss collisions. We're only discussing, so the final moment is the moment just before it is about to collide with the plate. So the final velocity is not 0, because quite often I see, especially in physics 1, when students are still learning how to model, of course, they make this mistake sometimes. So velocity is not known, so it means that two unknowns in one equation is not good. So it means there is only one equation left for the position. And the final position we actually do know, it's D. So that's our equation, right? So let's use equation for x. X, it's a final, so x naught plus v naught t plus at squared over 2, and acceleration is positive, so no troubles. Okay, so now let's simplify. X naught, we started from the origin. We released an electron from the origin, so x naught equals 0. Initial velocity also, it is released 0. In final position, the final position at the positive electrode, so x is d. Acceleration, we just found. So let me just solve it first for t with a, and then on I will plug in acceleration, expression for the acceleration. So t will be equal to square root of 2d over a. You see, this is 0, so I just move 2 to this side, 2d, and then divided by a, and square root. So and now let me plug acceleration. Of course, magnitude of acceleration. So it will be square root of 2d and divided by u over m epsilon naught a. And now let me just make it look nice, because right now it's going to look ugly. Not wrong, but not pleasant. So 2m epsilon naught a d divided by product of charges. Okay, let me check my notes to make sure that I didn't. Yeah. Otherwise, I would get really embarrassed to make any mistakes in a problem like this. Yeah.
Are we given the kinematic equations on the formula sheet?
They are there, I think, right? I need to check. I keep adding change there. Oh, you have a computer. You have that open file. Yeah. So next one. It's a little bit lengthy, but ideologically quite straightforward. So now let's solve something similar, but now using the energy approach. The recent stuff when we introduced this potential energy, energy of interaction. So let's solve that problem. Actually, it's almost from your homework. Just one student came to me, I think yesterday, with that question, right? So I decided, yeah, why not? Let me discuss it. Okay. So again, parallel plate capacitor, and I will try to recycle the picture. Recycling is good. So use this. Yeah, actually, it's so this situation, let me first describe it in words. A parallel plate capacitor, electric field is not given, distance between plates are not given, so we only know that if you take a proton and release it from the positive electrode, of course it is going to accelerate, it's going to fly this way, accelerating. And let's say we know the final velocity of the proton just before it is going to collide with the negative electron. So we know only final velocity of the proton. Then, if you take now an electron, negatively charged object, and release it from the negative electrode, of course it is going to fly in a similar way, but in the opposite direction towards the positive electrode. So now we need to answer the question, what will be the final velocity of the electron just before it collides with the positive electron? Positive electron. So now let me probably move it slightly lower. So first proton. Let me use. So it starts from here. It's a proton. Initial position of the proton. Initial velocity is zero. And of course it travels this way. So we know, you know what? No, let me label initial velocity of the proton is different. So V, IP or PI? IP. IP equals to 0. I stands for initial, P proton. And okay, let me write here. It's a proton. And the final velocity of the proton is given. So VFP. So essentially, what is given? Let me write it explicitly. So VFP. That's it. Only one number. Actually, in your problem, in homework problem, number is given. I decided not to give any numbers. So then, as I said, the second particle is an electron. And it is released from the negative electrons. So let me first write it. It's the initial position for the electron. And the IE equals to 0. So, and of course it is going to travel this way. So this will be the final position. And we need to find, so it's a final position. And we need to find the final electron. Yeah.
Are those two particles at the release at the same time?
Are they related at the same time?
Like are they released at the same time?
It doesn't really matter. You can release it at the same time. You can release them one by one. Pretty much you just need to know information about the proton experiment in order to find something about the electron experiment. Right? Essentially, you have two experiments, but if you want to run them, if you run them at the same time or separately, it doesn't do it. Okay. I guess you know. I understand your question. Are you asking? Are they going to interact with each other?
Possibly.
No. Gigantic distances between them. Or you can shoot them one at a time. Right? So no interactions between each other, between those two particles.
Is it because like the charges are relatively small and the distance is relatively big, so the force is basically non-existent?
Let's say one at a time, right? So first proton, second experiment electron. Right? And so let me write what we need to find. V final of electron. And two approaches. Energy approach, no, force approach, which we just discussed, can be used here, or energy. So now let's apply an energy approach. Since the force approach we already discussed. Which is based on the conservation of mechanical energy. So it will be E initial equals to E final. I wrote it sort of on the side because it looks like we need to apply that conservation of mechanical energy how many times? Obviously twice, right? For an electron and for a proton. So let's start with the proton. So P. And then E. So for proton, so it will be E. Which subscript I use? Initial first. E equals to E F P. Again, I stands for initial, F for final. P proton. And the same for an electron, so it will be initial electron equals to E final electron. So I'm just evolving them at the same time, dragging them almost simultaneously. Right? So now, of course, kinetic plus potential, kinetic plus potential. So it will be kinetic initial of the proton plus potential initial of the proton equals to kinetic or final of the proton plus potential final of the proton. Now, let me write something similar for the electron. So, kinetic initial of the electron plus potential initial of the electron. Kinetic final of the electron plus potential final. Final of the electron. Started feeling dizzy with these subscripts. No, seriously, right? Okay, so now and I will keep moving. I still have enough space, right? So. Okay, explicitly. Now we have to be careful. So 1/2 mass. Mass of the proton, mass of an electron are different. So make sure that you will add subscript next to that, because I remember when I started solving on the piece of paper, I also kind of first forgot about different masses, different particles. So this will be MP. Then initial velocity of the proton squared, then plus potential energy. We have point mass inside of a parallel plate capacitor. So that's the potential energy expression. U equals QES. So let me over here remind. So it's QES. So Q of the proton, electric field. Do I have to put any subscript next to the electric field?
No.
Of course it will be stupid, right? So because they're exposed to exactly the same electric field, right? So. Then initial position of, did I use S? No, I think I used X. Forget about this S. So X. I try to follow the notation of the book, but sometimes I kind of, let me use X. It's more convenient. So X, so it's a initial position of the proton. So equals now a very similar 1/2 mass of the proton, velocity of the proton final squared, and plus QE X final of the proton. You know, let me write very similar for the electron, and then we will start actually applying what is given about this or that value. Right. So 1/2, pretty much it's exactly the same, but instead of P, I need to write E. So mass of an electron, velocity initial of the electron squared plus. But now I realize that it's not exactly the same. What is different? Except for I have to, of course, change the subscript P to E. On purpose, right now I stopped because I realized that I need to make some additional adjustments.
Minus Q.
Electron is a negatively charged object. We need to show that, right? So let me put minus Q, right? Minus Q. And of course, charge of the proton in absolute value exactly the same as the charge of an electron. So now I will put minus Q E X initial electron equals to 1/2 mass of the electron V final electron squared plus plus minus Q E X final of electron. Phew, you really feel like dizzy. Okay, so now let's start simplifying it. But we need to be careful. Where is initial, where is final? Initial velocity of the proton? 0. Initial velocity of the electron? Exactly the same story. They both released. But I didn't want to dump it immediately. I just want to show that those terms and then start simplifying. Then, initial position of the proton. Now you have to be careful because I'm sure if I give a problem like this, there will be lots of mass with the initial and the final positions. Initial position of the proton. Initial position of the proton. D. Then initial position of the electron. 0, because yeah, electron starts from there. So picture is essential, so you can look quickly, all right, and realize what is the correct. So 0. Then final velocity is given. That is our unknown, global unknown, which we need to find at the very end, right? Then final position of the proton, 0. Final position of the proton. Proton is over here. Final position is 0. And final position of the electron, D. Finally, electron is over here, which is D. Because they basically travel in opposite directions, right? So now, now let's rewrite in the simplified, the simplified version. So it will be QED equals, okay, let me just rewrite because it's too messy. QED equals to 1/2 mass of the proton V final proton squared. So it's the first equation and the second. 0, 0 equals this and minus, so it will be 1/2 mass of the electron V final electron squared minus QED. So, strictly speaking, how many unknowns do we have in this equation? Masses are given. We assume that you can open the book. I would be even greedier, kind of, but of course we can. Now it's a number of questions. It's so first of all, of course, final velocity of the electron. Then electric field is now also not given, and the distance between the electrodes also not given. So it looks like 3. But since electric field and D, they basically goes together like twins, right? Siamese twins, right? Connected, right? So we can treat them basically as one unknown, right? Or in the simple words, we can say, come on, we just combine this equation or connect them through QED, because QED here, QED there, so we can connect them, create one equation through that QED. So let me make it sort of clearer. So from the first equation equals, I'm just rewriting the first equation without any changes. And the second equation will be QED equals to ME final electron squared. So if left hand side is exactly the same, right? So I just move this to that side, this plus. So it means that the right hand sides are exactly the same. So it will be 1/2 m electron V final electron squared equals to 1/2 m proton V final of the proton squared. Almost there. So again, this is our unknown, right? So this is given. Masses are also given 1/2 Gauss, and as a result, we're getting that velocity final of the electron equals to square root mass of the proton versus mass of the electron, and V final of the proton. Did I jump over too many steps? That's good. So this is essentially a homework problem. But of course, numbers are actually given. I prepared another, it's very short, about 2-point charges, and again, energy approach. And yeah, this is the last one. And actually, it was on the exam in spring 2020. You know what? I will write underneath. So 8, number 8. First, I thought about skipping it. So, two equal charges. So we have two Q's. So initial position, situation. So here charge Q capital, here charge Q capital. Distance between them is D. Then final situation. Of course, okay, let's assume this charge is stationary. Let me write it's a stationary. So, the second charge, of course, is going to be repelled because they are equal. Right? So it means that this charge is going to fly away. So, this is still Q, and this will be over here, and the distance between them 4D. I already restarted. Right, so then, initial velocity of this charge, I think, is 0, right? Yeah. This, the initial equals to 0. So what needs to be found? Velocity of this charge at the final situation. So first, this is stationary, this is also. So we release this. Of course, it will start flying because this charge repels that one. Of course, it's going to accelerate, accelerate, accelerate. And let's say we know that at this moment of time, when the distance between them is 4D, let's say I want to know the velocity of that charge when the distance is 4D. So, given D for D and charges. So we need to find that D. Actually, in this case, energy force approach is more complicated, right? At least in my recitation classes, we did discuss that. We will do it on Monday. Yeah.
For the second, like the final condition, the left Q is like fixed, right?
Stationary.
That's fair.
I didn't want to write one more time stationary.
Okay.
It's stationary. It's ground, nailed. So energy approach. So now again, the energy. In this case, energy approach is way better, easier. So the total mechanical energy over here must be equal to the total mechanical energy over there. So I can write so E initial equals to E final. And again, Q initial plus U initial plus U initial equals to K final plus U final. Which formula for the potential energy must be used now?
The one for the point charges.
For point charges. Because again, sometimes I see if a few times I give a problem like this. Sometimes students just use the wrong formula. It's not good. Okay, so I will probably be able to write over here. So it's 1/2 m masses. Yeah, masses are given, assume. So let me write actually what is given. So you know what it makes sense. Given Q, M, D. So all those are given. Okay, so 1/2 mv initial squared plus K. Charges are the same, so Q times Q, Q squared. Divided by initial position, distance between them is D. You know what, probably I should write which formula because we use U equals K. U over R. So potential energy. First power of R downstairs. So in this case, then equals to 1 over 2 mv final, okay, final without subscription, squared plus k q squared over 4d to the power of, wait, you didn't see this. Come on, we use Coulomb's law too much, right? So it's a force of habit sometimes, just brain without, no, hands without communicating with your brain write something. Alright. Okay, initial velocity, 0. And that is our unknown, right? So, let's rewrite it. So it will be 1 over 2 mv squared equals 2. So this will go to that side with minus. So it will be k q squared over d minus k q squared over 4d. I was quite surprised that it is from the exam, as I said, 2 years ago, 2.5 years ago. At this point, I realized that quite many students not comfortable with dealing with the ratios. So when they needed to subtract this 1 minus 1 over 4, sometimes they would just leave the answer like this. So sometimes some mistakes, right? So be careful, right? So you just need to bring it to the common denominator. So this must be multiplied by 4, divided by 4, and almost done, right? But I was quite surprised by that. So let's multiply by 4. And here by 4, common denominator, and of course as a result, we're getting 3, so it will be 3ku squared over 4d. Okay, so now that 2 and mass goes to that side, and as a result, okay. Let me continue here. So it will be v equals 3, okay, times 2 k q squared divided by 4 md. Of course, 2 and 4 partially cancelled, and as a result, we'll get 3 k q squared over 2 md.
Shouldn't it be square rooted? Oh, never mind.
Actually, I was trying to first write this squared and then take next step. I would erase squared, put a square root sign like I do in my recitation classes quite often. But as a result, my hand did something which, again, without proper communication with my brain. All right. So v equals q can be of course factored out, but since there are no numbers, so we'll just keep everything under the square root sign. Square root of 3k q squared over 2 md. Again, numbers are not given, so pretty much that's our answer. In this case, energy approach is the approach, because if you try to apply force approach, in this case, actually it's an example where acceleration over here is not going to be Gaussian. And as a result, kinematic equations you can say bye-bye. And yeah, just a second. So I gave this this problem again, as I said, 2 years ago, and yeah, most of the students just aced it without sometimes explaining too much, right? But that's another story.